Welcome everybody to the session number 3, and we're going to start with one of our keynote presenters. So we have Pierre Lanari starting off, and he'll be telling us about some of his X mapping tools and how we use it. So, where you go, Pierre.
Excellent. Thank you very much. And thank you also for the invitation. It's really great pleasure to present this research in front of such a broad audience. So yeah, to them, I'm gonna try to integrate part of the complexity that we observe in natural rocks, for example, compositional zonings of minerals, into the most popular petrological model that we use for thermobarimetry. Those are equilibrium phase diagram of pseudo-section. So those diagrams, they are the results of a forward model, and the forward model tends to reproduce the natural behavior of a metamorphic rock, to minimize its internal energy and to reach thermodynamic equilibrium. So one way to minimize the internal energy of a rock is to adjust mineral assemblage, the mineral modes, volume fractions, and the mineral composition. And those outcomes of metamorphism of observations, they will reflect the temperature, pressure conditions of mineral formation and the bulk rock composition. So the way we usually use those models, we take an on-size specimen of rock, we separate into 2 pieces. The first one, we make a rock powder, we analyze to get a representative bulk rock composition of our sample. And this is the input of our forward model. On the other side, we make a thin section, and from the thin section, we export the observations that are the mineral assemblage, mineral modes, and mineral compositions. And then there are 2 what I would call limits to this approach. Is first, we often have a partial comparison between the mineral assemblage, mostly, and a few diagnostic phase compositions, such as isoplates, when we compare our observations and the results of the model. And the second limit is this is not, in practice, it's not from the same volume of rock. And when we look at also now, we have the CT scanner, we can see how the mineral modes are changing at the centimeter scale. And one could wonder when we see the result, what is a representative bulk rock composition. So we came with Eric Duesterhoeft to an alternative strategy, and we call that iterative thermodynamic models. And the idea is those are hybrid models. They are based on the forward model, and the idea is to compare the observations and the outcomes of the model quantitatively to create a misfit parameter. And if you minimize this misfit, you can optimize pressure, temperature, and eventually some components of the bulk rock composition. But as I have shown before, this doesn't work if you use a bulk rock composition, because you don't have the matching observations for the same volume. So we propose the idea to use quantitative compositional maps, then to take a domain, and from this surface or this small volume, we can extract a consistent local bulk composition and the observations, and they are from the same volume. Questions that remain, and I want to quickly discuss today. The first one is, how do we investigate the rocks at the thin section scale, and what are the advantages? How do we run iterative thermodynamic models? What can they do? The main question is, we use local bulk composition. Is that relevant when we study natural rocks? And can we apply this technique to natural rocks? So let's start with the first question. How do we investigate the rock quantitatively at the thin section scale? So we use the software solution I developed a few years back now, XMAP tools. And I'm sure everyone here in the Zoom has already once in his life collected these X-ray maps. This is an example of a silicon K alpha. You have an X-ray intensity for the color code. And we have about 240,000 pixels, 15 elements, and it takes between 1 night and a couple of days to collect one of these maps. And if you use XMAP tools, it's pretty simple. It's very few efforts to convert this map into a quantitative compositional map, for example, silica here. So you get the equivalent of 240,000 spot analysis, and you can extract local bulk composition. You can see the mineral zoning. This is an example of sodium content in atom per formula unit in Kleiner pyroxene. And the data processing takes maximum 1 to 2 hours. We are trying to reduce that. and you get all the information. So this knowledge, Mike was discussing about the paper of Cohn and Spear, the knowledge of how we measure the compositional variability of the mineral phases. So XMaptors can do a bit much more than that. There are many tools inside and visualization tools. And one of the recent functionality that we added to the software was to try to give some tools for modeling, and especially one tool to run those iterative thermodynamic models. So the program is called Bingo Antidote. It has two parts, Bingo and Antidote. It's integrated into XMaptors. It can handle compositional maps. It can handle compositional maps. You can directly select on the map a local area, calculate the local bulk composition. You can define the composition of your phases that you assume to form in equilibrium. And then the program runs the comparison between observation and models. But if one wants to do this comparison, we have to come up with a concept of a way to evaluate how they match. And we came up with this idea of model quality factors. Those are parameters ranging between 0 if the results are completely different, and 100% if we have a perfect match within uncertainty. And we have three factors: the QASM for the assemblage, the Q volume for the mineral mode, and the QCNP for the mineral composition. That you can combine them to get a Q total that would be your misfit parameter. So that's the first part, bingo. And Antidote provide a series of subroutines or optimization functions, for example, to find the optimal pressure temperature conditions, but it can also map the different objective functions, do some compositional optimization, textual investigation, and so on. But I want now to show you an example. How does it work? And the perfect way to start is to assume that the thermodynamic data are perfect and that we have a perfect sample for which we know the composition. So I'm starting with a theoretical example. I took this phase diagram from Chris Yakimchuk that is calculated for an average phyllite composition. And I took the model outcome at 650 degrees and 0.8 GPa as what would be our rock. So those are pseudo observation, fake observation. And we obtain a mineral assemblage, we obtain mineral modes and mineral composition. That's what you obtain at this PT condition. And then we can calculate a map of model quality factor for the area for the PT region here in the red, within the red rectangle. And this is how it looks like. You can see the QASM, value, it's simply calculated as the number of matching phases between model and observation divided by the total number of phases. So it's 100% in the stability, in the region, the PT region of the stability field of the assemblage. And if you change one phase, for example, if you add magnetite in the model compared to your pseudo observations, then the value of the model quality factor for QASM is decreasing. The Q volume is calculated only for the matching phases, so it's less sensitive to the assemblage. And we simply compare the predicted volume fraction for the model and the observation with a weighting term. And it is again 100% at the optimal conditions. And then you see that you have some variations around when, of course, we don't match as soon as we change the pressure and temperature conditions. So the third one is the QCNP for the mineral composition. So that's the total map. It looks like it's similar, like if you calculate all the isoplates for all the solid solution, and the intersection would be perfect in this case here. We can calculate QCNP for individual mineral phases by simply looking at the absolute difference in composition between the model and the observations. So we take the uncertainty we have from the electron microprobe measurement. If the model is within plus minus 1 sigma, that's the blue curve, then the model quality factor is 100%. If it's outside the 6 sigma range, then it's 0%. And the function, the shape here is controlled by the exponent in the equation. And we can sum up for every element and every mineral, and we obtain this map of model of QCNP that shows you the best intersection of all isoplates. Then, if we combine the three maps together, we obtain this map of Q total, and you see that the maximum value is 100% at our reference PT condition. So it's very easy for Antidote to invert this model, try to find the maximum value of Q total, and this would be the maximum PT conditions that you have in your for your sample. So this is what it is for this case. If we do the inversion, we obtain the original PT condition. All the model quality factors are 100% because we have perfect thermodynamic data and perfect measurement of the mineral composition. So if we go to a natural example, this is an amphibolite to granulite facies metaphilite from the Himalaya. Very simple mineral assemblage, garnet, biotite, feldspar plagioclase, and some silimonite and quartz. And if we map this sample, we take a domain, we extract the local bulk composition, we put that into a bingo antidote, and we say, okay, find the optimal PT condition. And you obtain something that is very close to the reference conditions that were obtained for this sample. So 800 degrees, 0.5 GPa. The QCNP is a bit lower than expected, but again, now we have the uncertainty. And as you can see, the observation in the models are pretty similar. So it's apparently a pretty good model. We can optimize some composition variable. Here, for example, is optimization of H2O, the amount of H2O you put in your local bulk composition. And it's similar to a TX diagram, except that this is a single PT. And you can see how the model quality factors are changing with the changing amount of H2O in the bulk. You can look at individual phases, for example, and you can also compare the volume mismatch between the model and the observation. As biotite is the only water-bearing mineral, the optimal condition should be where you cross zero in this diagram. So it's a nice example, and it seems to work pretty well, but there is one thing that I did in this example is I selected arbitrarily this domain. So I said, okay, let's focus the analysis to this spatial region in my rod, this area of interest. So one could wonder if it is really relevant to use a local bulk composition when we want to do this kind of investigation. So for that, to demonstrate that it is relevant, I'm coming back to this theoretical example. Now what I will do is we run a Monte Carlo simulation using 10,000 local bulk compositions that are generated using the mineral compositions predicted to be stable at this condition and variable modes. So we simulate the modes, and then using the mineral composition, we recalculate for each simulation a local bulk composition. And here you see an example how it looks like. This is the bulk rock composition. Then we have one simulation here with a lot of garnet, one with a lot of plagioclase, one with a lot of muscovite. And this is matching what you usually observe in natural metaphylites at this PT condition, that formed at these PT conditions. You have region with more muscovite, region with more plagioclase, and region with more garnet. So now for this PT condition, I'm calculating the Q total, so the model quality factor of this PT for all the simulation. And I'm showing you the results in a diagram that shows the amount of plagioclase that you put in your local bulk composition and the amount of garnet. And this axis is the Q total. And as you can see, for all the models, we get exactly the same result, and the Q total is 100%. And this is totally normal because what we change in the Gibbs energy minimization is only the mass balance equation. We don't change the energy of the phases by changing the modes. And if you look at this table, it shows you for a selection of simulations, the mineral compositions that are predicted by the minimization at this PT. It's again, always exactly the same, which means that if you investigate a well-equilibrated assemblage in your sample, as we have in this theoretical example, it doesn't matter if you use the bulk rock composition, if you use any local bulk composition, antidote will always converge to the optimal pressure and temperature condition. Something that is changing is the equilibrium phase diagram. So those are showing you the phase diagram for the selection of the simulations I showed you before. And as you can see, the geometry of the field is changing because many curves are controlled by the mineral proportion that we use to calculate this bulk composition. If you have a lot of garnet, garnet is predicted to be stable in the entire PT region. If you have less garnet, then you see the garneting curve here. And this is normal again, because in this example, what we do is we are interested in our well-equilibrated assemblage, this point in the diagram where all the models are identical, but around they are not. So it also means that our capability to estimate, for example, what would happen during prograde metamorphism in this rock are strongly limited by our knowledge of the reactive bulk composition. And if the reactive bulk composition is changing, the position of our reactions of the curves are also changing. So coming back to the example from the Himalaya, now we did the exercise to take several different local bulk compositions, and we obtained slightly different results. So the value of the Q total was changing. So we thought that this was because of the uncertainty that we have, for example, in the measurement of the composition. But in fact, it was a bit more complicated. And the way to visualize that is to look at the maps of the model quality factors. This one, the first one is the QASM, and you see the mineral assemblage, the PT region here, where we match our observations. And the Q volume, the maximum value is very close to 100% and is matching with these peak conditions that we determined. If we look at the QCNP, that would be the intersection of all the isoplates of how the minerals are modeled, we see that now we are higher pressure condition, a slightly lower temperature. So there is a mismatch. We can look at the QCNP maps of individual minerals. The core of the garnet shows condition at higher pressure conditions. The rim of the garnet is at the peak. Then we have biotite 1, biotite 2 at the peak. We have plagioclase that seems to be at lower temperature conditions, and sanidine as well. So we can sum up by saying that we obtain a quite nice pressure temperature pass for this sample with different minerals that form at different time, and they do not re-equilibrate, or all of them, at the peak conditions. In this case, we have about 50% of the rock, plagioclase, sanidine, on the interior of the garnet that is not re-equilibrated at the peak conditions. So how does that affect the model, in fact? How does that affect our capability to model the peak condition? And to answer this question, we can come back to the theoretical example, and we do the same exercise again to simulate 10,000 local bulk composition, but instead of using an equilibrium scenario, we use a disequilibrium scenario. So for the composition of the plagioclase that we use to calculate all the local bulk composition, we don't take the composition of the plagioclase at the peak, that is X albite 0.71, but we take a prograde plagioclase, as it was for the Himalayan sample. And then we see how the model at this PT will react to that. So I'm showing you again the results in the same PT space, space, where we have the plagioclase fraction we use in the local bulk composition, the garnet fraction we use in the local bulk composition, and now you have the QCNP values for plagioclase in blue, for garnet, and for staurolite. If we have a lot of plagioclase in the local bulk composition, the QCNP value is low, and it affects the garnet as well because there is calcium partitioning between plagioclase and garnet, and also therefore the staurolite, because garnet and staurolite they partition iron and magnesium. And if you have less plagioclase in your local bulk composition, the model quality factors are rising and they're getting more close to 100%. They do not reach 100%, except if you exclude completely plagioclase from the model. So it shows you that if you use different domains in your thin section, then you can see how the model quality factors will react to this selection. And it will tell you that maybe by using less plagioclase, you get a better model. Here for the bulk bulk composition, it will be about 22% of plagioclase, so the model quality factor will be quite low for this example. And plagioclase is quite often zoned. This is an example of a compilation of 3 maps of plagioclase composition X albite from peak condition. It's always metaphilite peak condition from 620 degrees to 820 degrees. And we see that we have compositional zoning all the time. I don't want to compare the absolute values of the compositional zoning, but how it looks like in the plagioclase. And plagioclase is not the only phase that is zoned, as it can be garnet, white mica, amphibole, and so on. So having said that, one can wonder if we can really apply this technique to the investigation of natural rocks. And to try to demonstrate that we can, and what does it bring to you, I want to show you a third example that is, again, a metaphilite, slightly lower pressure and temperature condition. It's a famous sample from the Central Alps because it was used by Todd and Ingi to establish the thermal gradient in the Central Alps during the peak Barrovian conditions. So the peak conditions, they determine about 620 degrees, 0.6 GPa. We have also some zirconium rutile composition. We have the monazite age that is 22 million years, probably dating very close to the peak conditions for this metaphilite. And it's a nice sample with, again, garnet. We have muscovite quartz, plagioclase, We have some kyanite in green and staurolite in yellow. Also biotite, but in biotite in this case. So we have different domains with different mineral proportions. You see again, muscovite rich, plagioclase rich domain. It's very similar to what I showed in the theoretical example before. So we can take the bulk composition, we can calculate a phase diagram, and it's quite nice that in the end we have this assemblage, this stability field that is exactly what we observe in this sample, that is matching the conditions of third domain. So it looks pretty good. But the problem is that there is no mineral that is correctly modeled, or no mineral composition that is correctly modeled within the stability field. Something obviously is not working there. So we can look at the compositional maps. This is the maps of garnet. We can distinguish 4 different garnet compositions. We can use some iterative thermodynamic models to model how garnet will form. This is a program we developed a couple of years back that can model fractionation and resorption of garnet. And if we do it for the 4 composition, we obtain this PT loop 1, 2, 3, 4 that is a different PT condition compared to the peak conditions that were determined before. There is zoning in plagioclase, also in muscovite. We have more phengitic cores with the muscovite-rich rim. And so what we did is to say, okay, let's have a look at the local equilibria that we can reconstruct in this sample. So we took a look at the mineral matrix, then at the domain where the kyanite formed around the garnet, so garnet kyanite assemblage. And the last one was the retrogression, was where chloride formed, and it's always associated to the position of staurolite. So those are the results for the 3 areas, of interest. The mineral matrix, we can model the assemblage we observe in the mineral matrix, because the model is very good for the local bulk composition of the matrix. We have Q values that are quite high, a bit below 90% for QCNP. And this is because the biotite and the plagioclase rim, they probably indicate, or they indicate those, the condition, the PT condition of the mineral matrix. But we see that muscovite and the interior of the plagioclase, they indicate higher pressure and lower temperature conditions. If we look at the kyanite domain, it's a bit more complicated because the garnet is not matching. The composition of the garnet in this area is not matching with the peak condition. So garnet was, or this composition is clearly out of equilibrium, probably re-equilibrated later on by diffusion. But for the biotite and plagioclase, it's pretty good. And again, muscovite is showing this lower temperature, higher pressure conditions. If we take the retrograde assemblage, everything is in a narrow PT region. We have biotite and garnet slightly higher pressure, but very close to the staurolite and the chloride. And something you can notice in these QCNP maps is that for chloride, we never reach a value of 100%, which means that we can't model, we can't reproduce with the model the chloride composition that we observe in this rock. So if I sum up everything, we obtain a bit more detailed pressure temperature pass with a mineral formation sequence with garnet 1, garnet 2, and plagioclase muscovite forming during the prograde, metamorphism, quite higher pressure, or more higher pressure than expected before. And then at the peak, we have kyanite, biotite, plagioclase 2, and some garnet, and we have a retrograde assemblage with garnet 4, biotite, chloride, and staurolite forming together. But one of the striking conclusions here is that 50% of the rock was not re-equilibrated at the peak condition. So in terms of volume, we preserved 50% of the rock that the phases were metastable at the peak conditions. We can also test to take different areas, as I did before, see if we can identify metastable relics to do it different than using the maps of quality factors. This is an example for the garnet kyanite domain. And as the garnet is out of equilibrium, in this case, more garnet you have in your domain, lower the model quality will be, less garnet you have, higher the model quality will be. So it means that if you just take your sample and say, okay, I have 30% of garnet with kyanite biotite, and you calculate the local bulk composition, maybe you are not at the optimal, or the model is not optimal for this PT stage. So to summarize, I had these 4 questions, and I showed you that we can use quantitative compositional maps to determine both the compositional viability of minerals and to try to interpret this compositional viability. We can estimate local bulk composition. We have developed a program being antidote to run iterative thermodynamic models. We demonstrated that it is always relevant to use a local bulk composition, even though it's not recommended to use, it is not recommended to use a bulk composition when you want to constrain a stage where you have a metastable relics. And we can apply this technique to the investigation of natural rocks, and it allows you to explore a region that you can't really explore with the equilibrium phase diagram. So this shows you your pseudo section that would be in this field where you assume equilibrium in all your sample. And then if you have a one phase that is out of equilibrium, what happens is you should start to investigate this big box here with the question mark. So being antidote allows you to try at least partially to investigate what's happening in this field. So I thank you for your attention. I'm very happy to take any question.
Okay, thank you very much. Pierre, you've finished in plenty of time, so we have time for some questions. So Barbara has Kunz has an essay here. So she points out that most of your examples are on subsolidus rocks. Have you tested this on, high temperature UHT, migmatites, things like that, where volumes of equilibration or whatever, or changing compositions often at a very large scale compared to a thin section?
Yeah, absolutely. So most of the examples are below at subsolidus condition, except the one from the Himalaya, where the plagioclase form, where you start to produce the melt, and then you preserve this plagioclase metastable until the peak conditions. There is about it's about 100 degrees. So this one melt was present when you started to form this rock. So it's in the granulite field.
Great. And Rich Palin has a question. How do you deal with the pervasive problem that equilibrium volumes are 3D in nature, but you're really using information from a 2D thin section? Is this how the Monte Carlo technique comes in? Maybe
yes, absolutely. That's the test, the Monte Carlo test. So if you consider that if the rock is really well equilibrated, then it doesn't matter if you look at it in 2D or 3D, because any domain you will take in 2D or 3D will give you the same model somehow. But we tried as well. So now we are trying to do it in 3D. So to take the input from the CT scanner to get the mineral modes, and then to recalculate how variation could affect the model. But in theory, if everything is perfect, it shouldn't affect.
Okay, and Lucas Chiavetti has a question, because we still have a bit of time. Does the current version of Bingo have functions to test Q's variation in non-equilibrium samples? That is where we have relics.
Yes and no. So it's not implemented. Let's say it would be possible. It would be a bit more complicated technically, because you need to make some assumption to eliminate parts of your samples or of your minerals. For example, you could say, I want to eliminate the interior of my garnet, but this is something you should do before in XMAP tools before to send it to Bing Antidote. Okay. So yes, it is feasible, but it can be a bit tricky for a beginner.
Okay, I got one question myself. So if we're dealing with a rock that's high temperature, how selective can you be with what elements you really want to deal with your quality of the composition? Because yeah, you might want to do aluminium, but you really don't want to bother with how well iron and magnesium in OPX, for example, matches anything, because it's going to be reset. So can you say, okay, really, I want to do composition of these three elements, and I really don't care about the rest. I know they're stuffed.
So yeah, this is a very good point. Of course, iron magnesium would reset and be reset. So yes, you can do that. So there is a way to say I want to optimize only based on the X. For example, in clinopyroxene to look the X amphosite, X jadeite in clinopyroxene. That's feasible. Yeah.
Cool. Okay, thanks, Pierre. I think we move on to the next talk.